In regards to continuity, there are three requirements that are necessary in order for a function to be continuous at a point. So we're looking at a function f. We want it to be continuous at a point x equals a. So in the previous video, we discussed the idea of how the limit and the function have to be one and the same. In other words, the behavior of the function as x approaches the point must be the exact same value as the function's value at the point, because the limit doesn't care about what's happening at the value of x. It only cares about what's happening near the value of x. Whereas the value of the function, well, that is the value at x. That's what its sole purpose is. So it's not concerned with what's near it. It's only concerned with what's going on at the value. So we want to make sure that they're connected. So let's talk about the three requirements, and we're going to work it on an example as well. So requirement number one is that the function must exist at the point that we're interested in this case, the point x equals a. So our first requirement is that f of a exists. Now, in order for us to work that out, we literally just have to show that we can get a value for the function at the given x value. So if we go to our example 24, which is in your notes, we have f of x, a piecewise defined function. What that basically means is that that function is going to follow one of three possibilities depending on the input. Well, our goal right now is to show that the function exists at the point we're interested in. We're interested in showing that f is continuous at x equals 2. So our first requirement is to show that f of 2 actually exists. And this is rather easy, right? Because we see that when x is 2, the function is 1. So by writing down that f of 2 is equal to 1, you are showing the AP reader that the function actually exists at x equals 2. First requirement is done. Second requirement is to show that the limit as x approaches this value, in this case 2, over here in general a, right, that limit must exist. So requirement number 2, the limit as x approaches a of the function exists. That's what we have to show next, right? This is a little bit more work, because in order to show the limit exists, we need to show that the limit from the left exists, the limit from the right exists, they're the same value, and if that's the case, then the limit will exist. So over here, with our example, number 24, again, our goal is to have the limit as x approaches 2 of the function. That needs to exist. Okay? Well, in order for us to do this, we have to check the limit as x approaches 2 from the left, and the limit as x approaches 2 from the right. We have to do both sides, both one-sided limits. If we get the same value, then the limit will exist in general. So when we're talking about the limit as x approaches 2 from the left, we are discussing numbers that are just below 2, like 1.9999. 1.9999 is less than 2. So we're going to use the top function there. We're going to use 2x cubed minus 15. So when we're finding this one-sided limit, we know that we can punch this number in. Even though it's 1.99999 that we're interested in, that's so close to 2, we can use 2. So we're going to plug 2 into our function. And we have 2 times 2 cubed minus 15. We know that 2 cubed is 8. Double it to 16. Take away 15. That means that our limit is 1 as x approaches 2 from the left. Now let's look at 2 from the right. 2 from the right means functions that are bigger, or values of x that are bigger than 2, like 2.001. That's bigger than 2. So we have to use our cosine function. This, because that's how a piecewise defined function works. So the cosine of pi x, which means we're going to plug 2 in for x here, just like we did the recent limit. Cosine of 2 pi. You studied the cosine function in pre-calculus. Cosine and sine, they have a revolution of 2 pi units, which means that the cosine of 2 pi is the same value as the cosine of 0. Cosine of 0 is 1, so this is equal to 1. And you can verify that on your calculator if you're still a little rusty on your trig values. So the limit as x approaches 2 from the left is 1. The limit as x approaches 2 from the right is 1. Both one-sided limits are heading to the same value. That means that the limit exists in general, so that's good, and it's equal to the same value. So the limit as x approaches 2 of the function is equal to 1. That's what we learned about earlier in the year when we talked about symbolic limits. That checks off the second rule. Now we get to the third one. The third one is that the value of the function at x equals a must be equal to the limit of the function as x approaches a. Two have to be equal to each other. So that is to say the limit as x Otherwise, we have what's known as this little hop in the graph. Okay. Well, what's going on here? Here's our value of our function. It's 1. Here's the limit. It's 1. So how do we show this to the reader? Well, the third requirement is that these two have to be equal to each other. 1 has to be equal to 1, which is a true statement. So yes, you literally have to write 1 equals 1. But that will get you the point on the exam when they ask you to prove that something is continuous. So when you're showing that a function is continuous at a point with these piecewise defined functions, sometimes you're not going to get that middle function. Sometimes you'll have something more like this. Okay? And if that's the case, it's not all that big a deal. Okay? So when you do the limit from the left, it's still going to be the top function. When you do the limit from the right, it's still going to be the bottom function. When you're finding the value of the function, well, it's actually going to be the same as the limit from the right because we have this greater than or equal to. All right, so you end up doing the same work twice as you're showing that, say, the function exists at a point and one of the one-sided limits also exists. You're going to be plugging 2 or whatever the value happens to be into that exact same function to show that both of the items are in fact true. But whether it's a 2-part piecewise defined function or more than 2, like we had with 3 or even 5 or 6, it doesn't matter. You just check the value of the function. You check the limit as x is approaching that value, and if they are the same, then you have a function which is continuous at that point.